Okay, how are we doing today? Today we're going to move on in stoichiometry and do some problems with how to go from like a mass to a formula or percentages to the formula. This has to do directly with the lab, the hydrate lab that we were doing. So it is one that you're going to want to take notes, write down the notes, because you're going to have to replicate this process in the lab. Okay? All right, so first things first, what's IUPAC name of the following compound? I will give you a hint. The compound has a transition metal in it. All right, and I will ask you this on Edpuzzle, but Mn is manganese, O is oxygen, so it's manganese oxide. All right, because it has a transition metal in it, it's not going to be covalent, it's going to be ionic. And because it has a transition metal, we have to have the Roman numeral for its oxidation number. So in this case, it'd be manganese, Roman numeral 3, oxide. Okay? All right, so here we go. How to determine formulas from percentages. You can also use this for grams as well. It just eliminates the first step. But percent to mass, mass to moles, divide by small, multiply to the whole. All right, percent to mass to moles, divide by small, multiply to the whole. So this is kind of a phrase or saying that will help you remember what to do and when to do it and get you through the problem. All right, so you got to be able to go from the percentage to the mass. Once you have the mass, or if you don't have percentages and they just give you masses, you just skip the first step. Then you go mass to moles, and then you will divide by small, which we'll know what that means in a minute, and you multiply to a whole if needed. All right, sometimes that last step is not needed, but it just depends. All right, and this is a way you can think through this logically. I've learned over the years that this little saying is helpful for most students. Okay, so a compound consists of 72.2% magnesium and 27.8% nitrogen by mass. Asking, what's its empirical formula? Okay, so the first things first is you got to take these percentages and get them into a mass. Now, there's lots of ways to do this. All right, there's what I call the easy way, and then there's what I would call the hard way. All right, you can figure out 72.2% of any number and 27.8% of any number if you want to do that. Or you can assume you have 100 grams of the compound, then it becomes very, very simple. All right, so assume you have 100 grams. So in this case, if you have 100 grams of this compound, then 72.2 grams would be magnesium and 27.8 grams would be nitrogen. You basically take the percent symbol and replace it with the grams. All right, that's the easiest way to do it. There are other ways, but I don't know why you would do it any other way. All right, so now once we have grams, the next step says mass to moles. All right, so take our masses here, 72.2 grams of magnesium and 27.8 grams of nitrogen, and convert them to moles. And this is just how we've done it all along. To go from mass to moles, you divide by the GFM of the relative thing. So in this case, that's magnesium and nitrogen. All right, so you got to convert to moles. All right, so it's 72.2 divided by the mass of magnesium on the periodic table, which is 24.3 grams. Okay, and then nitrogen, you're going to do the same thing, but you're going to use the mass of nitrogen off the periodic table, which is 14. All right, so you go 72.2 divided by 24.3. And rounding becomes critical. Realistically, it should be sig figs, but since these numbers have 3 digits, these have 3 digits, then round your answer to 3 digits. Remember, 0.001 is only 1 digit, even though it has 3 things you wrote down. All right, or actually 4 things that you wrote down. Zeros in front of the number never count. That's when you get into trouble with sig figs usually. All right, but in this case, when you round to 3 digits, you get 2.97 moles. Okay, and you're not going to necessarily get whole numbers, and that's okay. All right, and then 27.8 divided by 14 is 1.99 moles. So that's mass to moles. So we did percent to mass here, just converted from percent to grams. Mass to moles, so you do the normal mole formula, divide by the GFM. Okay, now we have to divide by the small. And what that means is you're going to take the numbers you have. In this case, we have 2 numbers. Sometimes you might have 3, sometimes you might have 4. 4 is usually not very common. But you're going to divide all those numbers by the smallest number that they give you. So in this case here, we have 2.97 and 1.99. I think everybody knows that 1.99, oh, ignore that there. I forgot to take that off. Divide them by the smallest numbers. All right, magnesium and nitrogen. So these are the numbers I had from the previous slide. You're going to divide them both by 1.99. All right, the nice thing about this is one of them is always going to be the number 1. So in this case for nitrogen, it's going to be 1. And for magnesium, it's going to be 1.49 moles. And then the nitrogen is going to be 1.00 moles or 1 mole. So I rounded these both to 3 digits. All right, now if we stopped here, we would get a formula. What this means is this is the mole ratio of magnesium to nitrogen in this particular compound. So you have 1.49 moles of magnesium to 1 mole of nitrogen. Now, I think everybody's aware of the fact that we can't write a formula with a decimal point as a subscript. So we can't stay here. So in this particular case, we have to multiply till whole. You don't always have to multiply till whole. All right, but in this case we do. So, and when you do have to multiply till whole, you start with the number 2. You multiply them both by 2. If 2 doesn't work, you multiply by 3. If 3 doesn't work, you multiply by 4, so on and so forth. All right, so here we're going to take the magnesium and nitrogen. So magnesium is 1.49, the nitrogen is 1.0, and you're going to multiply these till whole. So I'm start off by trying to do it by 2. So I'm going to multiply them both by 2. And when I multiply these both by 2, I get 2.98 and I get 2.00. All right, whatever you do to one, you've got to do to the other. That's because this is the ratio of the magnesium to the nitrogen in this particular compound. So you can't change that ratio. We can't just multiply one of them by 2 because that would make us get an erroneous formula of the compound. Okay, so now this number is not exactly a whole number, but it's pretty darn close. And for our level of chemistry, we're going to use 0.2 as our cutoff. Anything within 0.2, we will call it a whole number. So if this was 2.81, we would still call it a whole number. If it was 3.15, we would still call it the whole number 3. All right, so for our level, we're going to call anything within 0.2 a whole number. That's going to make life easier for you in a lot of ways. Okay, so what this tells me is that magnesium is going to have a subscript of 3, and nitrogen is going to have a subscript of 2. So you get Mg3 N2. And that's the final formula of our compound. So that's how we took the percentage of elements in the compound and got to a whole formula for that particular compound. And this is stuff that's actually done. There's actually instrumentation that like you can put a compound in and they'll give you the relative percentage of elements or polyatomic ions in some cases in that compound. And then you can calculate and figure out what the compound actually would be. Okay, so that's all what we're doing. And that's the basic process. We'll go through a couple of practice problems. I think I'm going to have to write on a piece of paper because I cannot, this program does not work well with writing with a mouse on here. So here's the problem. A student determines that a hydrate of barium chloride is contains 14% water. And they want to know what is the actual number of water molecules relative to the barium chloride. So what we're going to do here, and what I'm going to do here is I'm going to go to this thing. Hopefully this will work. Why does it look like it's not working? Okay. All right, it is working. So we've got barium chloride. We're going to write in green and blue. And I just got to find where this is on the screen. Get it in focus. Okay, so there we go. We got barium chloride. I'm just going to zoom out a little bit. I think that's a little bit small. Okay, so we've got barium chloride. And they told us in the problem that 14% of it was water. And this thing's not focused. Trying to get it focused. Here we go. Okay, so I'm just going to flip back at the problem. They tell us 14% of this compound is water. So what that means is you got barium chloride and dot something in here. You've got some amount of water. And in the problem, they're telling us this amount of water is relatively 14%. Okay, so first things first, we have to get the formula of the compound. You look up on your reference tables, barium is a +2, chlorine is a -1. So you crisscross, jump, and you get the formula of the compound to be BaCl2. Okay, and because it's a hydrate, it's going to have this dot here. All right, and then what we have to figure out is what relative number molecules of water it has for a barium chloride particle. So you're going to get some whole number here. Like, you know, if it was 2, it'd be dihydrate. If it was 3, it'd be trihydrate. If it'd be 5, it'd be pentahydrate, whatever it is. All right, so I wrote it as water there, but it realistically should be .H2O. So some number of water. Okay, so when we're doing this, and this is just like the lab, you're going to, instead of breaking this down into elements, we're going to write this as barium chloride. We're going to write it as a line, and then we're going to write water. Okay, we know 14% of this compound is water. Okay, so if 14% of the compound is water, then the rest of it has to be the barium chloride. So you subtract from 100, and you'd find out that 86% of this is water. Okay, they do have to add up to be 100, so just make sure you do that. So now what we have to do is we have to go percent to mass, mass to moles. All right, percent to mass. So all we have to do here is literally just change this so this is 86 grams. And then for the water, it's going to be 14 grams. All right, a periodic table would probably be helpful for you. I'm just opening mine up right now as we talk here. So now we need to divide, we got grams, so we've got percent to mass, mass to moles. Now we got to divide by the GFM. Now water, I'm assuming you know that water's GFM at this point in time is 18.0 grams per mole. All right, it's 1 oxygen and 2 hydrogens. If we write the formula here, I could have wrote the formula there instead of the word. All right, so 2 hydrogen, 1 oxygen adds up to 18 grams per mole. Barium chloride. All right, I'm just going to come over here to the side. I'll do it in a different color. We've got barium. We've got chlorine. All right, we got 1 barium. We got 2 chlorines. Chlorine, I know when you look up on the periodic table, is 35.5. All right. Barium, when you look up barium, is 137.3. And that's the mass. So now we do the math. Sorry, my hand covers up. I'm lefty. We write backwards and cover it up. So 137.32 times 35.5 is 71.0. And when we add this up, we get 0.3. All right, we've got 8. We've got 0, 208.3. And then I'm just going to squeeze in the units over here, grams per mole. So for the barium chloride, we have to divide this by 208.3 grams per mole. Okay? So that's really step 1 and 2. All right, so now I'm just going to do the math on the calculator. Let's see if this calculator screen will show up on here for you. So we're going to take 86 divided by 208.3. That's going to give us that number. So I'm just going to round that to 3 digits. So after the 2, I look at the next number, it's an 8. So that's going to be 0.413. So this is going to be 0.413 moles. And then I'm going to do the same thing for the water. The water was 14 divided by 18. So 14 divided by 18 is 0.778 when I round it. Okay, so that's percent to mass, mass to moles. Now, I'm just going to come down here because I don't have enough room there. So I've got my barium chloride again. I've got my water. I've got 0.413 moles. I've got 0.778 moles. All right, I got to divide both of these by the smallest number. So in this case, I'm going to divide them both by 0.413. All right, so this is easy. This is going to become 1.00 and then 0.778. So clear this, 0.778 divided by 0.413, and you get 1.88 as your number. Now, because this number is within 0.2 of a whole number, we're going to push this to be 2.00. So what that tells me, so back in our original compound, if I can get, yeah, perfect, I can get them all on here. All right, for every 1 particle of barium chloride, I have 2 particles of water. So realistically, I could write a 1 here. I'm not going to write a 1 here, but I am going to write a 2 there. So it's barium BaCl2 dot 2H2O. So that's barium chloride dihydrate. Not that you would have to name the hydrates, but they're really not hard to name. Okay, so that's one of those. Okay, so now let's go back to our notes. I'm just going to bounce back and forth so I get the problem from my notes. So that's that one. All right, so here we go. We got calcium chloride hydrate. It has a mass of 4.72 grams. After heating for 7 minutes, the mass of the anhydrate is found to be 3.56 grams. Use the information to determine the formula of the hydrate. So here we go. So calcium chloride. Oh, I wrote on there. I just gotta get another piece of paper because it bled through. So I'm just gonna kind of split screen this right now until we get the info for it. Calcium chloride hydrate. So if crisscross jump, calcium chloride is going to have a formula of CaCl2. I'm not going to go into that right now. And we want to know what number of hydrate it is. So we want to know what would be on this liner in front of this water. All right, so here they tell us the hydrate has a mass of 4.72 grams. So the hydrate and they tell us the anhydrate or the anhydrous stuff. So I'm just going to write anhydrous is 3.56 grams. Okay, and that's literally all the information you need to determine it. So I'm going to get rid of the problem here. I'm just going to go up to the next one. Let's see, I just did it right there. Okay, I'm going to make this bigger. So a hydrate is this with water in it. The anhydrous is just this thing. So the difference is water. So water is going to be the difference between these two. So I'm just going to plug into my calculator. You could do the math the old school way if you want to, but you can use a calculator, so you might as well use a calculator. And minus 3.56. And you get 1.16 grams. So 1.16 grams of this compound is water. So, if we want to write this like this, kind of, you can see up here, this would be 1.16. And then the hydrate would be, or the anhydrous would be 3.56. And then the whole thing would be 4.72 grams. So it's kind of 3.56 grams of it is the salt and 1.16 grams of it is the water. So now what we want to do is we got to figure out like a mole ratio is essentially what we're doing. We got percent to mass to moles and such like that. So here, the nice thing is because we already have grams, we don't have to go percent to mass. We can just use the grams. So what I'm going to do here now, screen show up pretty? Yeah, we'll write it in right now. All right, I'm going to do calcium chloride and water. Okay, so calcium chloride is the anhydrous stuff. So I have 3.56 grams. The water we know is 1.16 grams. Okay, so that's percent to mass to moles. All right, so the next step, so percent to mass is done because we've already got grams. You could convert it to percentages and then convert it back to it, but it doesn't, it's an extra step. So now we go mass to moles. So for water, we have to divide water by its GFM, and hopefully, like I said before, at this point in time that water's GFM is 18 grams per mole. All right, we'll do that math in a second. We do have to get the GFM of calcium chloride. All right, so over here to the side, I've got calcium, I've got chlorine. Chlorine, there's two of them. Calcium, there's one of them. I know chlorine is 35.5. 2 times 35.5 is 71. Calcium, I have to look up on the reference tables. You can see right there, calcium is 40.08, but rounded to the 10th. Calcium's right here is 40.1 grams. So that's 40.1. You can add these up or you can use your calculator. Because everything's lined up, I'm just going to add them up right here. And then that's 111.1 grams per mole. Okay, so for calcium chloride over here, we have to divide that by the 111.1. Okay, so we just come in with our calculator, and I think I can get the screen up here. Perfect. All right, so we get 3.56 divided by 111.1. And then I get a calculator screen that looks like this. So now I want 3 digits. So the zeros in front don't count, so I'm going to go 0.0320. 0.0320. All right, and that's going to be moles. It's grams divided by grams per moles. I'm going to leave you with moles. All right, I clear it. I'm going to do the same thing here. 1.16 divided by 18. So once again, I got to go with 3 digits. So the zeros in front don't count. So it's 0.0 and then 644. Okay, percent of mass, mass to moles. Next step is divide by small. So once again, I'm out of room on this. So I'm going to come over here and I'm just going to continue carrying this down. Calcium chloride and water, because it's easy to keep them together like this. I'll just draw a line so it's kind of like a separate thing. We got 0.0320 moles, and we've got 0.0644 moles. All right, percent of mass, mass to moles, which is where we are. Divide by smallest. So we got to divide both of these by the smallest number here. So in this case, it's 0.0320 moles, and then 0.0320 moles. The nice thing is this number is going to be 1. Don't even have to do anything with that. And then the water in this case, we're going to try to get this on here so we can see it. 0.0644 divided by 0.0320. And then you're going to get 2.01. So that's close enough to 2 to call it 2. So what that tells me is in our original formula, if we can get this in here, I think we can. So for every 1 particle of calcium chloride, you have 2 particles of water, or 2 molecules of water. So the calcium chloride dihydrate. It doesn't work out that they're always a 2. I just happen to pick problems that they're both a 2. I do apologize about that, or gave you data for that. Okay. I just want to check something here. So here we go. So this is one that's not a hydrate one. So this is just using it. I don't think so we'll just do it. I'll write it out. So I'm going to leave this here. I think it's easier for me to write it out than for you guys to follow along there. I'm going to grab another piece of paper. It's going to have to be not white because I don't have any more white paper right here. Sorry about this. We'll go green. So we got a compound that contains potassium. So I got potassium, which is K. I've got sulfur, which is S. We've got 156 grams of potassium. And we've got 64 grams of sulfur. Okay, so now I'll just blow this up. Okay, so here, so percent to mass, we've already got it mass, so we don't have to do that. So we can just go from grams to moles. So for this, for potassium, we have to get the mass of potassium off the periodic table. All right, I'm going to put it up here. If it'll come into focus, I don't know. I think it should. All right, so potassium, you look right here, is 39.0983, which rounded to the 10th is 39.1. So you're going to have to divide this by 39.1 grams per mole. And then sulfur over here is 32.065, which rounded to the 10th is 32.1. So percent to mass we didn't have to do. Mass to moles, we're setting up right here. So now we just do the math. All right, so you've got, let's see, there we go, you can see it now. So we got 156 divided by 39.1 is 3.99. And that's moles because grams will cancel out. And then we've got 64 divided by 32.1 is 1.99 moles. Percent fast mass to moles, divide by small. So you're going to divide both of these by the smallest. When you're not doing the hydrates, you can usually fit it into one line. You're going to divide both of these by 1.99. This one conveniently going to be 1, works out well. 3.99, I think we can do that math without a calculator, but I will still plug it into a calculator. Is 2.01. All right, close enough to 1 to call it 1. So what that means in this case is that K is going to have a subscript 2 and S is going to have a subscript 1. We can write it like that. I will never write it like that. I will just go K2S. Okay? All right. All the problems, and you're going to get some homework problems to do these. Hardest part is starting them usually. If you weren't engaged in thinking and writing, it's going to be a challenge. But from here, it's just practice on your part. Stay in the Zooms and ask questions, and we should be good. You should be good to go with these things. All right. Have a great day.